So now that we have a general overview of a 3D moment, let's talk about mathematically how we're going to deal with that. So in the classroom, I usually would ask you what kind of formula do you know to calculate the components of a moment. But here in the online lecture, we can't do that. So let's just state that the component form or the Cartesian form of a moment, let's call it M about any point P, can be found through the determinant of R cross F. And of course, these are vectors, and the moment is a double vector. So please keep that in mind. So the first thing I write down is that my moment about point P is really equal to R cross F. And now how do I find the determinant of two vectors? And again, in the classroom, we could play this game for some time, and we could throw in different opinions of what is easier to solve this. But the one that we usually end up agreeing on in the classroom is the one that we have this I, J, K matrix, and then we put Rx here, Ry here, and Rz here, and Fx, Fy, and Fz here, and then we find the determinant of this construct. And that is how it's usually spelled out. But the question is, how do you solve this? And yes, some of you use calculators to do that, and that's absolutely acceptable. The only problem with calculators and solving equations and determinants and so on is once you make a mistake, a single mistake, so let's say you punch this number in incorrectly, then everything else comes out incorrectly, or everything that depends on this number. And then there's no partial credit. So my goal here is to show you one method that I see usually never go wrong on the exam when students study that. And therefore I encourage you to do that. I say it again, you can use whichever method you want to use to solve this determinant. But you know, it is just sometimes very susceptible to mistakes if you use a plug and chuck method. So I rather like to write it out. And so I'm going to show you how I usually do it. So let's give us some space here. So I copy this again, I, J, K hat. And then I have Rx, Ry, Rz, Fx, Fy, Fz. And then I bring my bars down here. And what I do next is I copy this first two columns behind it, so I and J, and then I use Rx here, and Ry here, Fx and Fy. And now it's a pure geometry construct that I just have to memorize that what I call the downwards diagonals, and I understand that diagonals always go down and up, but this is the one that goes from the top left to the bottom right. That is a positive diagonal, and so is this one, and so is this one. And I will talk about these in a second. But I also have upwards diagonals, so those are the ones that go from the bottom left to the top right. And I have one here. And I have one right here. Okay, and now I need to understand that the blue ones, the ones that I drew blue here, those are all positive diagonals. So I'm going to indicate them as positive, whereas the ones that go up here, the purple ones, those are all negative. Now, what do I have to do? I don't have to remember anything else. I just have to sum up what's going on that diagonal. So for example, here I have Ry, Fz multiplied, and this is my positive I component. And I have Rz, Fx, which is my positive J component. And I have Rx, Fy, which is my positive k component. Now the diagonals that go upwards, or the negative ones, which I have ry, fx, and again this is a negative, which is already indicated. The next one, oh sorry, I need to mention that this here is k head, of course. The next one would be rz, fy, and that is the I diagonal. I'm going to put the negative up here because it's far away from the diagonal. Last but not least, I have rx, fz, and that is my j component, and this is also negative. So let's keep in mind that these are all negative, whereas the ones on the bottom are all positive. And so what do I have to do now? Now I have to collect terms, and we will probably initially disagree on the outcome of this formula. But if now I want to calculate my m about that point P, what I end up with is first the blue component for I. So that was ry, fz, and keep in mind that was positive. And the other component for the I direction is given up here, right? So that's rzfy. So let's write that down. Minus rzfy. And all of this together, and I'm going to put a positive here as well, just to make sure that we understand the difference between this positive and this positive, because this is for the diagonal, this is for the general term. So all this is multiplied by I hat. Now I can give myself another positive value and go ahead and collect the blue term first. So rzfx, and this is also positive, and minus, be careful now, the j component is rxfz, and this is all the j components. And last but not least, the k component, where I start with my blue component again, rxfy, positive, minus ryfx, and this is now the k component. And of course, as we talked about in the last lecture, the entire thing, the entire construct here has usually a force times lever arm times distance unit. So therefore, we now have the entire formula. Let's talk about this for a second, because some of you will be surprised that I see a positive identifier here. You may think, in high school I learned that this term here must be negative, but this is incorrect. Not that you did it incorrect in high school, but the way these diagonals work out, and this negative here and this positive in here, make sure that this positive applies. And this is easier for me to remember than using something non-systematic. This is true for all terms here. I highly recommend that you follow this formula. And let's say, for example, you have a negative value here, let's say ry, then of course ry in here would be negative, but you would find another ry. So for example, here this would be negative, and then you obviously make sure that you stay consistent with that. But generally, this is probably the easiest formula to follow and remember. So I highly encourage you to do that. Some students think it's a burden to think of this as a new thing when they use the minus here, or they want to save some time. Instead of writing this down, they want to do this in their head. I think 2 seconds, or let's even say 2 minutes for this, would not be a waste of time, because it guarantees the right result. All right, now let's make sure that we remember that what we were really after for all this. So we used on the previous page the moments that were in 3D. So remember that this here was mx, this here was my, and this here is mz. And you can really see that right? So number one, you can see y, so it has obviously the j component, which is y. But then look at it. You have fx times rz, or rx times fz. And so you see the rule that we learned in last class still applies, right? So you have all three identifiers, y, x, z, z, x, y. Or let's take a look at this one, x, y, z, x, y, z, it applies. ZYX, ZYX. So it always works, and I highly recommend that you understand the physical meaning of these. And so let's remember that the moment about the x-axis is described by this term, the moment about the y-axis is described by this term, and then last but not least, the moment about the z-axis is described by that term. But of course, we can use this with our regular vector knowledge and calculate the moment's magnitude, right? The moment's magnitude is nothing else than mx squared plus my squared plus mz squared. And I think I explained that a few times, that you can always use Pythagorean in 3D. So here you have that once again, just as the magnitude of the moment. And that means also that you obviously can calculate the moment as a unit vector, and that is nothing else than mx vector about m as a total, right? And that's I hat plus my over m magnitude, j hat plus mz over m magnitude k hat. And let's talk about the units here real quick. Of course, the unit vector is unitless by definition, whereas, of course, the magnitude here must be in force distance. That is no different from anything that we have done before. Last but not least, let's talk about the fact real quick that you can also calculate alpha, beta, and gamma, which is the direction of these different moment components, and there's nothing different than before. So we have the cosine inverse of what, mx over m, which you can tell comes directly from the unit vector, right? So just the cosine of this value here will give you alpha, or the cosine inverse, and the same is true for the other ones, so I don't even have to really elaborate much on that. But of course here we would have my over m, and then we have, last but not least, mz over m. And that concludes how to theoretically define the moments in 3D. You now have methods to reliably calculate all the individual components. You understand where they are and what they're acting in which direction. You can also calculate the total magnitude of the moment in 3D, and you can describe its direction either by the angles or by the unit vector. That really makes no difference. As you can tell, it's kind of the same mathematics. So this concludes our theory part, and we now move on to solving example problems.